Hi guys, in this video we'll take a look at representing the product rule, integration by parts, definite integration by parts, examples, and then we'll finish with a summary. Let's revisit the product rule in order to get a rule for integration. So far we've looked at cases where the products of functions can be integrated using the reverse chain rule or a substitution. So we have seen that we can integrate functions like 2x multiplied by x squared plus 1 all cubed by using the reverse chain rule. We let f of x be the function x squared plus 1, and then we have f of x all cubed, and we have this multiplied by f prime of x. As indeed, if we differentiate x squared plus 1, we do get 2x. This is called the reverse chain rule, and we have seen it previously. Similarly, if we need to integrate something of the form x multiplied by the square root of 2x plus 1, then we perform the substitution u is equal to 2x plus 1, and we follow that through until we get a function in terms of u that we can integrate, and then we return back to x's. This is called the method of substitution. However, we are still unable to do integrals of certain products of functions. For example, how about the integral of x multiplied by cos x? Or how about the integral of x squared multiplied by e to the power of x? If we wanted to do a substitution for the first one, what would we substitute? And in the second case, there is no way to choose a function f of x in order to make the reverse chain rule work. To be able to integrate such products of functions, we need to look back at the product rule for differentiation. The product rule is as follows. If we differentiate with respect to x, two functions u and v multiplied together, so we have uv, then this is equal to u multiplied by dv by dx, and then plus v multiplied by du by dx. We can see that the terms in the original product are differentiated individually using this rule. So we have the terms u and v in the original product, and these terms have been successfully differentiated in this rule. These are the terms du by dx and dv by dx. We can integrate products of functions by considering integrals and derivatives of individual terms using what's called integration by parts. If we want to integrate the product u multiplied by v, then it turns out we have to consider the derivative of u du by dx and the integral of v with respect to x. So what exactly is integration by parts? We derive a formula for integration by parts directly from the product rule. Again, we have the derivative of uv is equal to, by expanding out, u multiplied by the derivative of v plus v multiplied by the derivative of u. We can integrate this with respect to x. When we integrate the left-hand side, because integration and differentiation are opposites, we end up with uv on the left-hand side, and on the right-hand side we end up with the integral of u multiplied by dv by dx, and then we have the dx, and then we add the integral of v multiplied by du by dx, and then we have the dx. We then rearrange this equation and we make the integral of u multiplied by dv by dx the subject. And therefore we have the product u multiplied by v minus the integral of v multiplied by du by dx. This is our formula for integration by parts. The integral of u multiplied by dv by dx is equal to the product uv minus the integral of v multiplied by du by dx. This allows us to find integrals we were previously unable to do. For example, consider the integral of x multiplied by cos x. What we do is to choose u and v appropriately so that we get the left-hand side expression to be the integral of x cos x dx. One possible choice is that we choose u to be equal to x, and then we choose dv by dx such that dv by dx is equal to cos x. By these choices of u and v, we end up with the product x cos x on the left hand side, and we can evaluate this using the right hand side, and hopefully we'll get something simpler. The first thing to do is to find v based on our definition of dv by dx. All we have to do is to integrate, and we get sine x. You may have noticed we're ignoring constants of integration for the moment. They will come in at the end. And so, in computing the integral of x cos x and using our formula for integration by parts, we will get the product uv. Well, u is x and v is sine x, and so we get x multiplied by sine x, and then our next term is minus the integral of v du by dx multiplied by dx. So we subtract the integral of v, which is sine x, and then we multiply by du by dx. Well, u is equal to x, so du by dx is equal to 1, and so we just have multiplied by 1 and then dx. This is equal to x sine x for our first term, and then this is just the integral of sine x, which with the minus sign becomes a plus cos x. And here is when we bring back the constant of integration plus c. There is a general strategy for choosing which function should be u and which as dv by dx. The strategy is as follows. When we are asked to find the value of the integral of the form x to the power of n multiplied by some function f of x and then dx, we employ the following strategy. We choose our u to be equal to this x to the power of n in all cases of f of x, except when f of x is the natural logarithm of x. For instance, we can use this method when dealing with the products of powers of x and trigonometric functions. Let's say we have the integral of x squared multiplied by cos x. We employ our above strategy. Because our f of x is cos x and not the natural logarithm of x, we're going to choose our u to be our x to the power of n, i.e. x squared. And as such, the only thing left to choose in our integration by parts rule is dv by dx. We choose that to be the other component of our product. And so we choose dv by dx to be cos x. Sometimes you may be required to apply the integration by parts formula more than once to fully integrate a product. If we look at our integration by parts rule, we have the integral of u multiplied by dv by dx, and this is equal to the product uv, and then we minus the integral of the other way round, v du by dx. Now, we were doing this process in order to simplify this integral on the left hand side and hence fully evaluate it. However, in the case that the integral over here cannot be easily evaluated, there are cases in which you have to apply integration by parts again to this new product. If we have a look at our new integrand in this case, what we tend to do is to then, if we're integrating again by parts, we let du by dx become our new u in the next integration by parts. And similarly, we let the v here become the new dv by dx in the integration by parts in the next integration by parts. So then we have our new u and our new dv by dx. These are both the new versions. And this, by the integration by parts formula, again, is equal to the product uv minus the integral of v du by dx. And then again, we may have to repeat this process once more, and so on. It all depends on what this integral here ends up being after performing the integration by parts. We are often required to integrate in this way more than once, when dealing with products containing integer powers of x. As we saw, we were looking at the integral of x squared, which is our u, multiplied by cos of x, which was our dv by dx. Again, we have this is our u, and this is our dv by dx. And this is equal to, using the integration by parts formula, we have u times v, which is x squared multiplied by sine x. This is because if dv by dx is cos x, then v is sine x. So again, these are u and v respectively. And then we minus the integral of 2x, this is our du by dx, and then we have sine x, which is our v. But as we see, the integral we end up with on the right hand side is not one we can compute straight away. Instead, we have to consider the integral of x sine x. And we use integration by parts on this again. So we let x become our new u and sine x become our new dv by dx. And so this is equal to our x, which is our u, and then we multiply by minus cos x. This is our v, if dv by dx is sine x. And then we minus the integral of 1, which is our du by dx in the case that u is equal to x, which we have here. And this is multiplied by our minus cos x, which is our v. So then this is equal to minus x cos x for the first term, and then we have plus, due to the two minuses, one outside and one inside, the integral of cos x dx. And now finally, this is an integral we can actually compute, and so we get minus x cos x, and then we have plus sine x, and of course we have our plus c. So now the integration is complete, we can return back to our original question, which was the integral of x squared multiplied by cos x, and this is then equal to the first term up here, which is our x squared sine x, and then we have to minus the other integration we did, which is the integral of 2x sine x, and because we have the expression for the integral of x sine x, we just multiply that by 2, so we want 2 lots of this expression here. So we have 2 lots of our minus x cos x, and then we have our plus sine x, and then plus c. Therefore we get x squared sine x, and then we have plus 2x cos x, and then we have minus 2 sine x. And then we're going to redefine the value of our c so that we end up with plus c. Technically we have a minus 2c, but again the value of c wasn't known before and it's still not known now, so we just have a plus c on the end, it's some constant. So how can we use integration by parts in order to calculate definite integrals? We have seen that when integrating indefinite integrals by parts, the result is an expression in terms of x. For example, we have seen that we can integrate x multiplied by cos x by parts. And when we do so, we get x multiplied by sine x, and then we get minus the integral of sine x multiplied by 1. And as a result, the answer is x sine x plus cos x plus c. But we note that this expression is an expression in terms of x. When integrating definite integrals by parts, we need to apply the limits of integration to each integrated expression in the result. So this becomes our integration by parts formula for definite integrals. The integral between a and b of u multiplied by dv by dx is equal to u multiplied by v, but this time in square brackets with limits a and b respectively. And then we minus, as we had before, the integral, but this time between a and b, of v multiplied by du by dx. In practice, we can calculate the value of the uv term with each application of the rule before calculating the additional integral. Let's suppose we are asked to calculate the integral between 0 and 1 of x multiplied by e to the power of x. Now, when choosing our u and v, we use the strategy that we discussed earlier, and as such, we let u be equal to x, and we let dv by dx be equal to e to the power of x. We can then find the corresponding du by dx and v that we'll need to apply the rule. So first, du by dx. This is just found by differentiating u with respect to x, and so we get 1. Similarly for v, we find this by integrating dv by dx, and so it's going to be e to the power of x. E to the x integrates to itself. And so we're looking for the integral between 0 and 1 of x, which is our u, multiplied by e to the power of x, which is our dv by dx. And by applying the integration by parts formula, we're going to get our uv, which is our x, multiplied by e to the power of x. And again, we need to remember to have our square brackets and our associated limits 0 and 1. And then we minus the integral between 0 and 1 of e to the power of x multiplied by 1. This is v multiplied by du by dx. And now we can begin to calculate the value of the square brackets straight away before evaluating this integral. So by substituting in a 1, we get a 1 multiplied by e to the power of 1, and then we get minus 0 multiplied by e to the power of 0, which is of course 0. And then we minus, well, the integral of e to the power of x is e to the power of x. And then of course we need our square brackets and our limits of 0 and 1. This expression on the left from the earlier square brackets is just e, and then we minus the new square brackets. Substituting in x equals 1 gives us another e, and then we minus the substitution for x equals 0, which gives us an e to the power of 0. The e's cancel out, and we have a minus e to the power of 0, which is a plus e to the power of 0, which is 1. That is the result of our integral. Now in this case, it looked a bit strange to actually evaluate this value before integrating this and including it inside that square bracket. But you could have calculated the integral first, and then just including it inside that square bracket and evaluating that all at once. It's entirely up to you. Let's take a look at some examples. Our first example asks us to find the integral of x ln x. Our first step is to recall the formula for integration by parts. The integral of u multiplied by dv by dx is equal to the product uv minus the integral of v multiplied by du by dx. Our second step is to choose the expressions used for u and dv by dx. We have the integral of x multiplied by the natural logarithm of x. Now, in our strategy we discussed before, we normally choose functions like x to be our u, but not if the function with it is the natural logarithm. And so we're going to let our u be the natural logarithm of x. And as such, we're going to let dv by dx be equal to x. Our third step is to find the corresponding expressions for v and du by dx. Since we have that u is equal to the natural logarithm of x, we can find du by dx, and just by differentiating the natural logarithm of x, we get 1 over x. Then we have that dv by dx is equal to x. And so by integrating this expression, we get that v is equal to 1/2 x squared. Again, we're ignoring constants of integration for the moment. Our fourth step is to find the integral, remembering to add the constant of integration. And so we use the integration by parts formula. We have the integral of x multiplied by the natural logarithm of x. And so we have the product uv, and u is the natural logarithm of x, and v is 1/2 x squared. And so we're going to get 1/2 x squared multiplied by the natural logarithm of x, and then we minus the integral of the 1/2 x squared, that's the v, and then we have du by dx, which is 1 over x. So therefore we have 1/2 x squared multiplied by the natural logarithm of x, and then we have this half x squared multiplied by 1 over x, and this just gives us a minus the integral of 1/2 x dx, and therefore as our final answer we're going to get 1/2 x squared multiplied by the natural logarithm of x, and then minus 1/4 x squared. And of course, because we're doing indefinite integration, we have a plus c. Our second example asks us to use integration by parts to evaluate the integral between 0 and pi over 2 of x sine x. Our first step is to recall the formula for integration by parts. We have that the integration by parts formula is that the integral of u multiplied by dv by dx is equal to the product u multiplied by v minus the integral of v multiplied by du by dx. Our second step is to choose the expressions used for u and dv by dx. We are looking to evaluate the integral between 0 and pi over 2 of x sine x. And so we're going to use our strategy mentioned before and let u be equal to x. And then we have that dv by dx is equal to sine x. Our third step is to find the corresponding expressions for v and du by dx. We have that u is equal to x, and therefore we can find an expression for du by dx by differentiating, and we get that du by dx is equal to 1. Similarly, we have that dv by dx is equal to sine x, and therefore we get that v is equal to minus cos x. Our fourth step is to write the definite integral in terms of square bracket notation. And so we have the integral between 0 and pi over 2 of x sine x. And using integration by parts, this is going to be equal to u multiplied by v, which is x multiplied by minus cos x. Now here we have to have our square brackets, and we have to have the limits of 0 and pi over 2. And then we continue with the integration by parts, so we subtract the integral between 0 and pi over 2 of v multiplied by du by dx. And so we have a minus cos x multiplied by a 1 for the du by dx. So then we get in square brackets minus x cos x, and this is between 0 and pi over 2. And then we have a plus, due to the two minuses, the integral between 0 and pi over 2 of cos x. And so finally, by performing the final integration and then putting it first, we get a sine x from in here, and we can put this inside the square brackets on the left hand side, and so we get our sine x from the right hand integral, and then we still have our minus x cos x. Our final step is to calculate the definite integral. We have the square brackets sine x minus x cos x, and the limits are 0 and pi over 2. This is equal to, by substituting in the pi over 2 first, sine of pi over 2 minus pi over 2 lots of cos pi over 2. That is the first bracket due to the first value being substituted in. And then substituting in 0, we have sine 0 minus 0 lots of cos 0, which is 0. Now, sine of pi over 2 is 1. Pi over 2 lots of cos pi over 2 is 0 because cos pi over 2 is 0, so that term disappears. And sine 0 is also 0, so the only term that counts is this 1, and hence that is the answer of the definite integration. Our third example tells us to use integration by parts twice to find the indefinite integral of x squared e to the x dx. Our first step is to recall the formula for integration by parts. We have the integral of u multiplied by dv by dx, and then we have our dx, of course, is equal to uv minus the integral of v du by dx dx. Our second step is to choose the expressions used for u and dv by dx. We're looking at the integral of x squared e to the x dx. And so in this case, it is sensible to let u be x squared and to let dv by dx be e to the x. Our third step is to find the corresponding expressions for v and du by dx. Firstly, we have u equals x squared, and this gives us du by dx as being 2x. And we also have dv by dx being e to the x, and by integrating both sides and ignoring the constant of integration, we get v as being e to the x. Our fourth step is to perform the integration by parts procedure. So by substituting into the formula, we have the integral of x squared e to the x dx, which is the integral we are considering, and this is equal to, we have u times v, which is x squared e to the x, and then we subtract the integral of v du by dx. And so we have e to the x multiplied by 2x. And of course we have our dx. Our fifth step is to choose again expressions to use for u and dv by dx. This is because we have our second integral over here that we can still not calculate without using integration by parts again. So by simplifying, we have 2 multiplied by the integral of x e to the x dx, and we want to choose u and v. So again, it's sensible to choose u equals x and dv by dx to be e to the x. Our sixth step is to find the corresponding expressions for v and du by dx. So in this case we have u equals x, and this gives us du by dx as being just 1. Similarly, we have dv by dx as being e to the x, so again, as before, we have that v is e to the x. Our seventh step is to find the integral involving the new u and v. We are looking at 2 multiplied by the integral of x e to the x. And so therefore, we can pull the 2 completely outside and just look at the inside integral, which, by using integration by parts, is going to be x multiplied by e to the x for our uv, and then we have to subtract the integral of v du by dx, which is e to the x times 1 inside the integral. This is going to be 2x e to the x, and then we have a minus 2 multiplied by the integral of e to the x. We know that when we integrate e to the x, we just get e to the x, so remembering the constant of integration, we're going to get 2x e to the x minus 2e to the x plus a constant. We won't call this constant c just yet, because we have another step to do, and that is to find the original integral by bringing the results together, remembering to add the constant of integration. So recall we had the integral of x squared e to the x, and we found this was equal to x squared e to the x minus the integral of 2x e to the x. Then we can use our above result, keeping the x squared e to the x where it is, but having the minus outside, because we know what the integral of 2x e to the x is as above. We can substitute it straight inside this bracket, and so we have inside the bracket 2x e to the x minus 2e to the x plus a constant. Then finally we can expand out this bracket, and so we have x squared e to the x, and then we have a minus 2x e to the x and a minus 2e to the x, and finally we can write plus c. This is because minus a constant is still a constant, and so we can just have our plus c on the end. And this is the final answer for our integration.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the snap and by smiley face, and together, let's make A-level maths a walk in the park.